Here we go. We have a classic applied max-min problem. We want to make a box out of a flat piece of tin that's 20 inches by 25 inches. The way we can accomplish that is by cutting out congruent corners or squares from each corner. Now, when I think about that, the smallest square I could make, if I wanted to think about it, mathematically would be 0. But if I do that, I'm still in a two-dimensional space. The largest I could make it would be 10 inches, but if you see, if I cut two of these out that are 10 inches long, then I'm back to a two-dimensional space. So my length of my congruent squares has to be somewhere between 0 and 10 inches. So what I can think about this is, well, if I don't know what it is, then it's going to be a length of x, right? So you can get this idea. I'm going to put a length of x here. And for some reason, it doesn't want to show this x there anymore. And to give you an idea, all these are lengths x. So that means that the shape of my piece of tin is going to change. These dotted lines represent where you'd fold the tin up. And you can imagine if I fold this side and this side, the reason we cut that out is these two sides, x, would meet. So knowing that we want to maximize the volume, we know that volume equals length times width times height. So I want to represent my length, width, and height. So in this case, my volume, my length, was now this dotted line, which means it's 25 inches minus this length x and this length x. So I get 25 minus 2x. My new width becomes, well, let me see if I can get 20 minus 2x, because I'm subtracting this length x and that length x. And my height is going to be this length folded up, which is x. Again, you could look, if I put 0 into here, 0 in for x, this whole thing becomes 0, so that it's not really a volume of anything. If I put 10 in here, 2 times 10 is 20, minus 20 is 0, and there's no volume. So it reinforces that this is the interval in which I'm going to focus. All right, how do I work with this? Well, I'm looking at the volume in terms of x, and I'm talking about maximizing the volume. So I want to know, when does the first derivative equal 0? So if I multiply this out, v of x equals, see, 25 times 20 is 500 times x. I'll get 500x minus 2x times 20 is 40x. 25 times 2x is negative 50x for a total of 90x. But I'm going to multiply it by x, so it's x squared. And now I'm going to take negative 2x and negative 2x, which becomes positive 4x squared times x, means it becomes cubed. Now I take the derivative. It's superscript. Here we go. V, let's get it on superscript. V prime of x will equal 500 minus 90x plus 12x squared. So I want to know, when does that equal 0? Because that's where my maximum or minimum will come out, right? And so looking at this, I know that everything's divisible by 2, so I can rewrite it as 250 minus 45x plus 6x squared. It'd be really nice if this factored. It doesn't factor, so I could use a quadratic formula. Or I could just get rid of some of these things. Could use my graphing calculator, which is right here. There it comes. Great. So I can come in and let me clear everything that's there. I'm going to go to y equals, and you can see it's already typed in. Okay? I can graph it, and there it is. So to find when x equals 0, right? To find when x equals 0, I'm going to find that this function equals 0 here and here. To find the exact values, I'm going to use these 0 functions. So I choose 2, and I follow the directions. Hold on, let me go back and do that. I feel like so that's for left bound. Let's find this one first. So a number to the left would be 0. A number to the right of this, not past here, might be like 5. And then I guess, and I find that it's 3.6811869. So I find out it's 3.6811869. Or x will equal, let's find this other one. So second calc, 0. I'm looking for a number to the left of here, but not past here. So maybe 5. A number to the right of that, which maybe is 15. And I guess. And I get 11.318813. Now, some of you might be remembering I can only use a length of that square between 0 and 10. So this should be my answer, right? But let's just test it. So I'm going to go back to my home screen, and I'm going to type in 3.6811869. I'm going to store it as x, and now I'm going to type in my function, 25 minus 2x times 20 minus 2x times x. And we find out that the volume at 3.6811869 is equal to 820.53 cubic inches. Just to prove that this doesn't work, if I go ahead and use that number, so I'm going to do the same thing. I'm going to go ahead, clear this, and I'm going to go ahead and type in 11.318813. I'm going to store it as x. The nice thing about my calculator is if I use the second enter key, it will start telling me what I typed in. There's my original function for the volume. So hit enter, and it will now use this value. And it tells me that the volume for 11.318813 is equal to negative 70.53, which cubic inches, which goes to show that there's no way that's possible. I can't have a box with such a volume. So my final answer to all of this is that the maximum volume of this box is 820 620 cubic inches when one side of the congruent squares is 3.6811869 inches. And this really is what I was looking for my answer. I hope that helps. With this diagram, we'll do a lot more and have some fun with it.